Okay, let me start by congratulating the organizers for conjuring up this very nice discussion meeting. Actually, India has an extremely strong optics community for very long time, and this meeting, the success of this meeting is a testimony to that, there are so many interesting topics. So we come into this topic of this conference as a lateral entry, because we use light. We use light for a lot of things, but our main interest is light matter interaction, and a very specific type of matter what we use is cold atoms. And so laser cooling and trapping is by now a very well established field. Bose-Einstein condensation and Fermi-degenerate gas, etc., have been seen. So what we work in Raman Research Institute is the cold atomic spins and interaction of the cold atomic spins of polarized with polarized light, and there are various interesting results what I will be talking about. Something what is the focus of this talk is these cold atoms in a structured optical potential. As you will see that many of this work is ongoing, and so since I was listening through this very exciting talks by previous speakers, and there was a lot of connections with the spin and orbital angular momentum of light, and I also wanted to present a few of our recent results with the atomic spins interacting with polarized light. So, okay, so we have several research programs at what we call QMIX group, quantum mixture group. So the main area is mixture of cold sodium and potassium atoms. So Sagar, who has now submitted his PhD synopsis, of course, yesterday you heard Sanjukta. She has a different experiment with rubidium Rydberg atoms. They are having fantastic recent results. And then Anirban, Gaurav, Shairi, and Swarnabho are new PhD students. They are in the lab nearly 1 year now. And so there was a poster outside about the trapped cold atoms in structured optical potential. I'm sure many of you had a chance to look at it. Gaurav is presenting this work, and if you have not, you can see the poster again. And Shairi, who has taken over from my previous PhD student, who is now a postdoc in Weizmann Institute on the spin noise spectroscopy with both cold and hot atoms. She is looking at quantum correlations between the spins of different atoms, and we have a very strong theory collaborator with Bimalendu, Sanjukta, and Krishnananda and Mugundan have contributed to that experiment as well in the past. So then if I have time, I will talk a little bit about the transport properties of cold atoms. In this, where one PhD student have already submitted his thesis synopsis, Shubhajit, and Anirban is taking over to really look into the quantum diffusion aspect of these. And then I have another primarily now theory work, and then the experiments will follow with Swarnabho, who is doing his PhD on this, which is closest to my heart. This is quantum magnetism and few body physics, and Shubhadeep De, whom some of you might know, is a collaborator in that experiment, and Sanjukta is also contributing. Okay, so I have highlighted a few of our recent results. Actually, we are a relatively new research group. Our experimental results, our experiment itself started commissioning around 2017, 2018, and then we have been looking into spin properties of cold atoms, and then the live spin interaction in cold atom via what is called a Faraday rotation fluctuation. And this is the outline of the machine what we have built recently, which will be the main playground in the next few years to come. So, talking about structured light, we are creating this holographic projection of laser light, which we also use for trapping and detecting the cold atoms in the lab. Recently, Raman Research Institute had 75-year celebration. So, Gaurav has kindly generated trapping light of the logo which was created, and this is our founder, C.V. Raman, and whose picture which is now projected, means we are planning to project onto cold atom. This is the trapping light structure of the of the uh, of the image. So, these are the things we are doing now. So, let me tell you the context why we are doing these things. So, traditionally this is a strong interest among the community in cold atoms starting in early 2000 to simulate complex condensed matter physics using cold atoms at very low temperatures of nanokelvin and even at microkelvin. The quantum properties dominate over the classical properties. The de Broglie wave lengths are much larger than the interatomic spacing after we cool and trap the atoms in our laser cooling and trapping setup, and these atoms can then be transferred into periodic trapping potential created by laser light, interference of laser light, and then people have looked into the superfluid Mott insulator type of transitions and various other exotic quantum phases which were directly observed for the first time using the cold atoms in so-called optical lattices. So, this is the traditional optical lattice which helps to simulate the condensed matter physics. So, I will not get into this because there are various research groups who have contributed in a decisive way in this field of research. Another, okay, so just staying on this, what I mean by this, so this kind of physics is comes under what is called Hubbard model, or a simplified form when bosons are in optical lattice. The Bose-Hubbard model, tunneling between the lattice sides are given by this term. The interaction, the on-side interaction is given by the second term with the atom number in each lattice side, and if there is repulsive interaction, then energy in 2 atom or even 3 atom in case of bosons or more, they shift from the ground state energy, and this is the interplay between the tunneling energy and the interaction energy. If the tunneling energy wins, we call it a superfluid, because then the atoms are free to move, it's like superconductor, and then if the interaction energy wins, then this is a Mott insulator.
Just a quick question. Where is that? What are the magnitudes of this J and U?
They can be tuned. They can be tuned to get into the strongly correlated regime. So in cold atom,
typical values you have?
Okay, so I have a slide later. You will see some values on that. So we can create what is called n equal to 1, 2, 3, and many Mott insulator state, and people have actually observed the superfluid Mott insulator transitions in traditional interference optical lattices. And then another point coming to, yeah, so another very interesting aspect is disorder. So earlier we talked about ordered, so the periodic potential, trapping atoms, and then looking into tunneling and interaction energy, and then what is an obvious ubiquitous present physics is disorder. It's everywhere, superconductors, graphene, photonic media, biological systems, you name it. And then the role of disorder is extremely important. This was recognized by people like Anderson and many other people. And then last year's Nobel Prize was given to Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. So this is also another very interesting subject to look at. Now, again, one of the achievement in the cold atom physics, the Anderson localization in disordered potential is first observed using cold atoms trapped in so-called speckle potential, quasi representation of a disorder, some kind of yeah, this is a Bose-Einstein condensate which is kept in speckle potential. Trapping light is passing through a diffusive glass plate. Yeah, yeah. So this were seminal work. One of the groups where I later joined as a postdoc. Very interesting set of measurements we did. So where various ways of creating this kind of quasi disorder potential, either using speckle or using what is called a quasi-periodic lattice. Some of you will recognize that this is described by something called an Aubrey-Andre model or a Harper model, and there is a quasi-randomness in space, and which also leads to localization, and this is an exponentially localized atom matter wave function, and this can be seen by absorption. I will show some example from our lab. Well, not of Anderson localization, but how we measured this kind of phenomena. So this has been what was going on in this field, and people are very excited. And then we looked into something, not again in my lab, one of my previous postdoctoral work. What happens when you put both disorder and interaction together? For example, you vary the interaction, coming back to your question, what are the strength of the interaction and what are the strength of the disorder. Disorder can be also parameterized by putting what is the speckle heights of individual scatterer, and then one gets into a very interesting physics which says that when you have a relatively low interaction and strong disorder, you go from an Anderson localization to something called a glassy phase. It's like puddles of superfluids separated by non-interacting regions. And then if you have a strong interaction and strong disorder, which is a regime which is not yet experimentally achieved, so then one can get into a mote glass type of an insulator. Anyway, so this is a cartoon. Again, some experiments were done. I was fortunate to be part of one where we looked into the momentum distribution of the interaction strain. So this is getting into your question. So the interaction in terms of tunneling energy, one can get into even of the order of 100. If Professor Gupta, this answers your question. Disorder also in terms of tunneling energy now can get into few tens, and then we can actually look into the that's the disorder strength. That's actually in some sense the fluctuation intensity in space. So now one can study the fluid insulator kind of phase transition, and this was done as early as nearly 10 years now. So now getting into the new regime. So there are still lots of open questions in this field. For Oh, so for example, okay, the blue, that means the momentum distribution is narrow. So you take a Bose-Einstein condensate, put it in the disordered interacting potential, you let it evolve. If it is a fluid, then the momentum distribution in space after you take a time of flight image will remain narrow, says that it's a fluid, you have a phase coherence. So those we are plotting as blue, and then when the momentum distribution becomes fat, that means coherence is lost, so that is more like red. So that's kind of a phase boundary. So this is just one snapshot from the work. So we looked into, for example, the breaking of the critical momentum. So that's a detailed work. So I just used it as a motive. This is actually each little the insight, yes, the insight is actually a time snapshot. Yeah. So it's interference experiment of the Bose-Einstein condensate, or if it goes to a insulating phase. So okay, so then of course those were quasi disorder. So yes, it is disordered interacting. So, sorry? Interaction we can go from weak to strong by what is called a phase-back resonance. So, for example, here this is a non-interacting, non-disordered regime. So, if you go to strongly disordered potentials, then this will be in the y-axis. If you now tune the phase-back resonance to go into strongly interacting regime, then you can get into a Mott insulator regime, and then when you have both, so then you can look into the entire phase diagram. But these things are done, but now of course there are questions like what kind of disorder you will call a true disorder. So, for example, those are artificial manifestation of disordered potential. Then how to measure the quantum phases. For example, in some sense what we always do in cold atom experiment, we prepare the cold atom sample, we shine resonant light, we kill it, and while killing we have a snapshot of a image which tells us which phase it was. So, it is not a non-invasive detection. I almost never liked it, theoreticians do not like it. So, we are trying to, not just us, many people are trying to develop what is called a non-invasive detection techniques for these cold atoms. They are really tiny and fragile objects, so it's not a straightforward thing to do. Then how to control interaction between atoms in an exotic way, like in true complex systems. In a true complex system, you just simply don't have inter-atom interaction. There are defects. You have to consider the atoms interacting with the defects. So that means you have to also consider the inter-atomic and intra-atomic interaction. So, all this motivates us to build a new experimental machine. So, this machine, I will say a few words about it. It's quite technical. Thanks to Sagar et al., the machine is built now over the past 3 years. So, we have a simultaneous laser cooling of sodium and potassium, because this allows us to also look into what is called impurity problem. We can have one species in the bath of another species. Now, the other species can be considered quantum bath, the let's say sodium and the potassium atoms which are cold moving around, they are like impurities. So, we can look into so-called Bose-Polaron problem. I am using lots of words, but so this is one of the motivation. So, we have demonstrated now last few months efficient production of cold atom mixtures, simultaneously cooling and trapping large number of sodium and potassium. We have an ultra high vacuum environment where we trap these atoms to protect them against the background collisions with thermal gas. That requires less than 10 minus 11 millibar of pressure. It's a technical word, but you imagine that entire room's air. Yeah. Yeah, it's very stable. Means it's stable in many ways. I'll tell you. So then we actually captured 10 billion or more potassium atoms and 500 million sodium atoms simultaneously. Now we are at microkelvin. We are making a few more progress to go into the nanokelvin regime. Then
why are the number of sodium atoms less?
Sodium is rather easy to evaporatively cool, but it's yes, it's not only do not need, there are technical issues about the first stage of cooling. So, we use potassium as a sympathetic coolant, so that's fine.
So, you launch the atoms in a boat, or?
I'll show you. Okay, so this is a bird's overview of our machine. We have two ultra cold gas sources. So, this we call sodium 2D plus MOT, and other side we have a potassium 2D plus MOT, and this is a two-dimensional cooling and longitudinal moving molasses, and then this passes through tiny holes in the vacuum manifold to be captured simultaneously in this 3D MOT, what we call chamber, and then there is an addendum which we are working on now to transport these cold atoms magnetically into what is called the science cell. So, these are the 4 chamber design of our vacuum assembly, and this Shairi had made a nice design of this two-dimensional cooling, what you were asking. So we create a cold atom trap which is transversely cooled in this vacuum chamber, and then we launch them longitudinally through a small differential pumping hole into the 3D mod, and that is somewhat related to another experiment of mine, which was the first BEC in India, where we had this kind of a design, and then we had a lithium potassium mixture experiment later on in Paris, where the similar design was implemented. Of course, we kept on making modification. Those are engineering modification, that's why I am not saying too much about it. So then this is a bird's eye view of, so we use a lot of lasers, optics for simultaneously cooling sodium, potassium, cooling lasers, repump laser, and we lock these lasers using what is called high resolution saturation spectroscopy, and then this is the vacuum setup. I think the resolution of the pictures haven't come very well, but anyway, so you can have an idea of what's going on here. All right, so I will go very.
Potassium, it is the D2 line you lock, or
Potassium we lock at the D2 line. Yeah.
hyperfine intervals are very, very small, right?
Yes, yes.
You resolve them.
Yes, we do resolve them. There are lots of tricks I'm avoiding. We can discuss. Yeah, because yeah, so both these atoms are not very easy to work on, but we do it because, not because we want to put ourselves under too much trouble, but to create a stable mixture.
And for 589, do you have a diode laser?
No, we have a what is called a 1178 laser, then we have a amplifier, then we have a bow tie cavity with the doubling, and then yes.
Why I asked you the question? The same mod is equally effective for both the species.
Coming, yes, good question. Okay, so after doing this, you can create these large blobs of cold atoms, which you can see here. So this is something like around 7 millimeter diameter cloud of sodium, and this is potassium. These pictures are taken with simple mobile phone cameras because we have so many atoms, they fluoresce so strongly, you can see them by eye. And then we do a lot of characterization, how we are trapping, cooling, what is the most optimized condition, because we are a bit hungry in terms of atom number, and because those are our signals. And then we do some other tricks which some of the experimentalists.
Can you go back to the previous slide?
Yeah.
So that clearly shows that the sodium has reached the more or less stationary state, whether it's potassium. The sodium hasn't reached the stationary state where the potassium.
Oh, no, sorry, I truncated the loading curves. Yeah, so this is.
It's still evolving, but this one has stepped certain. That's the reason I'm asking the question. Same mod can be equally effective for both the species or not?
I have a slide for that, and exactly to answer that. Yes. No, this is just, please pay attention that, I have just shown for the potassium, for example, for sodium, truncated loading up to only 1 second. If we load for a long time, they both, so they both stabilize, so this is not an issue. So we, for the people who wants to make similar system, we do another trick which is called light induced atomic desorption. We take the atoms which are going and sticking to the surface, shine them with an UV light, they again participate in the cooling process, and then we can actually keep on building up very large number of potassium and sodium atom. Both species work. This is actually a bit surprising to me, but this works good. So I'm not going to spend a lot of time on the.
Is that a UV lamp or a UV laser?
So we are using actually an UV LED, high power, yeah, kind of, along with the cooling and trapping laser. So then, of course, depending on many parameters of the lasers and the magnetic field of the trapping, this atom loading depends critically. So we have studied all of these things just for a sake of making the most optimized experimental machine, so that when we do more experiment in future, we don't have to worry about optimizing things. So this is under review actually, this work. So coming back to your question, Professor Datta Gupta, so when we have, let's say, just the sodium cold atom, these atoms load to some level. If we now introduce potassium later, there is a lag which I am not liking too much. Can I then use the pointer? Because yeah, yeah. Okay, no. So as we load the sodium atom, the yellow thing is sodium, and then if we allow potassium, what happens? These are very interesting phenomena. Once an atom goes to an excited state, P state, it becomes a fleeting dipole, and this dipole now tries to interact or induce another dipole in the nearby region, because they are all together. So potassium and sodium now will have a dipole-induced dipole interaction, and they try to kill each other. So we stabilize using various other laser parameter, trapping parameter, and so on. And then we can actually also calculate some other interesting phenomena, like the cold atom light-induced collisional stability, and this we have done last couple of weeks. And this gives us interesting insights also about the how these cold atoms interact with each other, some kind of a correlation, but I will again not spend too much time on this, so we can discuss definitely. Okay, so now I think the idea of using the phone was, so how do we detect? We shine a resonant laser light weak onto this blob of cold atoms. It casts a shadow, easier said than done. We actually image the shadow, and then on a CCD plane we see an absorption after a lot of imaging, and from the absorption image we infer all sorts of information: size of the cloud, how many atoms are there, what is the temperature, etc., etc. So this is our main detection technique. As you also notice that since these are resonant laser light, narrow frequency band, and this passes through a lot of windows in our vacuum chamber, so this also have a lot of inbuilt interference and diffraction pattern, which makes our imaging not so ideal. So Gaurav has developed a technique which is called sort of a Fourier component analysis in space to denoise the image. So we take the raw images which has lots of interference diffraction pattern. We run through an algorithm. I will not get too much detail into the algorithm. So this is actually a machine learning kind of an algorithm which recognizes the interference patterns which is there and the presence of the atoms, and then denoise this imaging, and we end up having a very nice signal to noise for this imaging. Some of the steps are given. We are trying to finish a publication out of this, and yeah.
Very interesting. So what is the iterative kind of cycles you use for this?
So I think you use something like 200 images, and then yeah, it's a computationally heavy thing, so we fought a lot to get some computational power. Yes, yes, but the algorithm itself allows for what is called a principal component identification. So we mask the cloud in one go, and then but this is, and also this helps us to do something which we are doing. Very few labs in the world has this kind of two species simultaneously trapped together, and we want to image them also simultaneously. And to image them simultaneously, just special filters are not enough. This we anyway use, interference filters, but on top of that we run this algorithm with two different fringe patterns imparted on sodium laser, potassium laser, and we see nice images. So let's, yes, this one is a representation with 18 image, yes. Okay, so now some technology. So what we are doing is that we also use a MEMS-based device, micro electromechanical mirrors, 3 micron size, 1000 by 800, and then we shine our laser light which interacts with atom through this, image the light onto the atom, and we can create an arbitrary trapping potential. We don't have to rely on the traditional interference based lattices. So we can create checkerboard, we can create, for example, wheels which can impart let's say slow angular momentum onto the atoms, and then we can also create. So this our imaging resolution is 2.4 micron. So the entire image we can put into that in principle. So here this image what you are seeing is the full frame. So from here to here it's like I think 3 millimeter. So but we image it, we focus it onto the atoms, and more interestingly what we can do, how can I get rid of it? Yes. We are looking at the Fraunhofer plane. So yes, this is DMD. This is the digital mirror device. So somehow this movie is not naturally playing. Okay, now it's playing. So we can also create, for example, and the timing resolution we have is of the order of 100 microsecond. So we can actually look into the dynamics that fast of the atom light interaction. And since these are cold atoms, they are not moving anywhere. They are moving like a.
The question is that you have control over this lattice size.
Absolutely. Yes, yes. So we, as you have seen, we can create any image. For example, we take a picture of yours and we can put it. So we have that kind of a control. And we are limited by the diffraction limit, of course, but then that is of the order of a micron. So this is why I'm learning and very much interested as close as diffraction limit if we can go. For example, with the tripod system. Okay, so going forward, so for example, these are some atoms trapped in a box-like confinement in our lab. This black region is actually that absorption image onto the atom. We can write some structure onto this. These are initial days of our work, and then we hope to.
So that the dark spot is for the due to the mixture.
This is the mixture of cold atom. This particular experiment, this is one species. It's a demonstration work. Then we are.
If you change the relative, the volume fraction of
Yeah.
the component,
It becomes improved.
change.
Which one?
This dark spot, does it change? Let's say you had this 10 billion,
Yeah.
10 billion sodium or whatever, I don't remember. Other one is 50.
Yeah, 5 billion, half a billion, yes.
If you change that ratio,
Mm-hmm.
does it get affected? This absorption spot.
Yes, it does, of course, because the trap volume and the density, everything is linked for this cold atom trap. Okay, so what are we planning to do in near future with that? We are presently writing structures on cold atoms and creating an algorithm for write and read protocols, for quantum information stored in trapped cold atoms, because we can write anything what we want.
Just one quick question. Experimentalists these days are very much interested in box potential.
Yes, that's why the box.
Is it box potential?
Yes, we can create box potential. It's rather straightforward. It's like a very high order Gaussian which gives you a flat top potential, and those mirrors can be arranged in a very clever way. Then we can create this. Yeah, this will be like a textbook.
Another side question, maybe absolutely irrelevant, I don't know. So let's say you create one molasses like this.
Mm-hmm.
You create another molasses.
Mm-hmm.
So you talk about this mesoscopic interaction between these two.
That's what we are doing actually.
That's what you are doing.
Yeah, yeah. We actually have a paper on that about how this response of these cold atoms in molasses, and we are actually looking into what happens when we have two molasses and how their response functions are changing. I think I will not have time to get into there, but I will show that it. Yeah, yeah, absolutely. Yeah, no, that's true. And we are actually solving, we have a strong theory collaboration with Professor Supurna Sinha, Rafael Sorkin, and we are taking their the Langevin equation, the quantum Langevin equation solutions to actually, well, now we are, that's the kind of work also we are doing. Okay, so now as I was saying, so most of these reading are in terms of the spins, atomic spins, and then of course we are also doing some kind of study what is called spin noise spectroscopy and spin correlation spectroscopy. This is what Shairi is doing now. So I'll go very fast. So this is my understanding of spins. Pardon me, it's quite rudimentary, but it works. So in atoms, of course, we have nuclear spin, orbital angular momentum of electron, electron spin, all of them together give us what is called the total angular momentum. These are all well known to us. Then this is one set of experiment what we had done with rubidium, which has a level structure like that in magnetic field, and then we are looking at the population fluctuations of spins in these magnetic substates. And what we are doing, okay, so these are the Zeeman states. I will not spend much time on here, you all know this. So we have these atoms, both thermal, one set of experiment we have done, and cold atoms where the spin populations are fluctuating. We are detecting those spin fluctuations. And how do we detect? This is what is called Larmor precision, you know. So what we do is that using the concept of Faraday rotation fluctuation. So Faraday rotation everyone knows, you send a polarized light through a medium and then the polarization rotates, absolute magic.
It does have some chirality.
Yes, it has in this sense. See, for example, if you send a linearly polarized light and then the magnetic levels are shifted, in that case one of the component, which is let's say RCP, is far detuned, LCP is near resonant. This you can engineer just by applying a magnetic field in case of atoms, and that means the phase shift of RCP and LCP will be different. And once the phase shift and RCP and LCP different, once they come out, then there is an overall rotation of the linear polarization vector. Okay, so then what we do, we look at this shift of the linear polarization by passing it through polarizing beam splitter and with two correlated detector, and then in a DC measurement you can always see that in presence of a non-zero magnetic field there is a shift in the signal, and you can easily measure the Faraday rotation. And for example, if you scan the frequency, that's another way of looking at it, you can actually see the Faraday rotation signal, which is the black one, as a function of the frequency from these cold atoms. Now, I'll go very fast. This is known physics. If you look at the fluctuation of the Faraday rotation, this gives us a lot of information, because I worry about noise a lot in the lab, and then finally made peace with noise, and we want to detect certain detectable quantity using noise. So this is known via the Johnson-Nyquist noise, that you can measure the resistance by just looking at the voltage fluctuation via the fluctuation dissipation theorem. So now can we do the same thing for the magnetization fluctuation? And it turns out we can. It took a long time to realize this. Now, if the population in these two states are fluctuating, even in absence of any external magnetic field, that will give rise to a fluctuating magnetization, and which in turn will give rise to a fluctuating polarization of the detecting beam. And this fluctuating polarization will be 0, average of this will be 0. But on the other hand, the second order time correlation will not be 0, and this is known via the Wiener-Khinchin theorem. And then in the frequency domain, we can actually expect to see a corresponding peak of the noise correlation, which is peaked at Larmor frequency at a given magnetic field, and which has a width which is known in condensed matter community as the T2 time correlation. In atoms also this is the case, but we have an advantage that this T2 is typically very, very high for atomic case. So that means these signals are very narrow. And so we do a measurement of this kind of polarization fluctuation. This is our data. And for rubidium, we do see extremely narrow noise line width. Of course, the signal strengths are very low. That is why it was not a very popular technique. Then we did some interesting stuff over the past year or so to enhance this signal, thanks to but before doing that, I wanted to show a few of the other things what we could do with this polarization noise measurements from atomic media. So we can use it as a very precise magnetometer. You can immediately see that all common mode noise are rejected, because we are always measuring the polarization fluctuation coming directly from the atom, which are sensitive to any external magnetic field, and this wins over so-called Faraday magnetometers. So this is a Faraday fluctuation magnetometer. So this is how we wanted to pitch it, one of our first initial measurements. And then what we did, we can reach actually to the present day competitive sensitivity of femtotesla per square root of hertz, not yet beating the traditional vapor cell magnetometers, because the signal levels are still low. But I'll show you some very recent modifications what we have done in the lab. So this also allows us to measure this rotation from the cold atom. So some interesting thing is that even at high field, these signals are available, which is totally not possible in a traditional Faraday magnetometer, because this is typically what is called a spin exchange relaxation free magnetometer, always near nanotesla. They have a sensitivity of 1 femtotesla per square root of hertz, but with the overall field of 1 nanotesla. Give them Earth's magnetic field, this is not possible. Okay, I don't want to be recorded, but here we can have a large dynamic range precision magnetometry. So this we have done. Okay, I don't go into detail again. I'm happy to discuss all this later on. So then we actually can even measure the tiny difference of the F equal to 1 magnetic manifold and F equal to 2 magnetic manifold, which is actually a measurement of nuclear G factor, by looking at the noise peak separating out, because these noise peaks are so narrow in kilohertz that we can actually measure them, and from there we had a relatively precise measurement of the nuclear G factor. So it's surprising that atomic physics experiment actually reveals the nuclear magnetic moment. Then of course we have looked at the vector magnetometry, and what is very exciting for me is this we discussed in this paper, is the time resolved magnetometry. We can actually see the variation of a magnetic field pretty accurately in a relatively short time of 100 millisecond resolution. So this is like faster than your heartbeat. So if there is a irregularity in your heart current, magnetic field can be measured outside. So lots of potentials to do that, because these dynamic measurements can be done because we are measuring fluctuations. Okay, so going forward, we have now borrowed an idea from Raman. We actually now do what is called a Raman drive between the spin states. I will skip this part, which is like a gravimetry measurement, what we have done with this technique. But then what I will just speak about is that, okay, I will also remove the vapor cell discussion. So what we do is that we can actually now shine a pair of Raman beams driving the two spin state non-invasively, and then look at the spin correlation of a driven system. So driven spin state system, and Bimalendu very kindly developed the theory for us. We published recently this result, and then we can actually show a million-fold enhancement of the signal, preserving the intrinsic nature of the spin noise signal. So we can actually have a.
Is this not like a lambda system?
It is a lambda system. Yes, but we have this this thing. So again, I'll omit a lot of details. I have shared the papers. You can go through or discuss with me. So what we have done, we actually have now shine this Raman-driven spin spectroscopy on cold atoms and demonstrate spin coherence lifetime of the order of a millisecond. So this is how we can see a very strong signal for the driven system for cold atom and extremely narrow. That means that 1 by T2 is this, so T2 is in the millisecond range. So if anyone wants to use the cold spins as qubits, then they can be preserved for millisecond, which is like eternity in this. Okay. So of course, Shayari has made a lot of improvement to do this kind of Raman driven spin spectroscopy in the so-called spin exchange relaxation rate free regime. So, and then we have recently seen a width reduction even further in this kind of experiment, going to a very low magnetic field regime. And there was a question about the response function. So we do shift the cold atoms from the trap center and look at its dynamics in presence of a molasse, and now we are looking at interspecies interaction dependent dynamics. So, so this is how we look at the position response function and the velocity response function of these cold atoms in the molasses. So, okay, so I'm sorry I took 3 minutes more. So I wanted to conclude that this is a new state-of-the-art machine to experimentally study ultra-cold atomic gases. Lots of things. I gave a novel measurement technique to explore spin dynamics, which is what we call the Raman-driven spin noise spectroscopy. Then these applications include quantum sensing with high precision and high time resolution. And then one what I did not discuss is an experiment to connect generalized Langevin equation treatment with cold atom measurements, and then cold atoms in structured potential. This is what is driving my research quite a lot now, and which is in sync with this. But this slide is very important. I must thank our workshop, Ibrahim, and Meena Shujata, who has been the electronic support, and administration for allowing me to purchase and not purchase many things I wanted, and all the funding support, and then also the Rydberg team who made a presentation yesterday that I did not talked about. Okay, so I'll take any questions you will have.
Thank you very much. Nice talk, reporting many new and interesting results, experimental results. So we can take two quick questions.
Yeah. So, hello. Yeah, my question is like in experimentally in optical lattices we use like this kind of cosine square, like two laser beam counterpoint. This is kind of cosine square form or sine square form. So is there any possibility with this instrument, that mirror instrument you are showing, no, this MEMS? So with this instrument we can manipulate this optical lattice, something like cosine form or sine form.
Well, that we anyway can do. See,
Okay.
in our experiment, we have a traditional optical lattice using a 1064 nanometer laser with interference and so on. So what this MEMS allows us to go beyond that. For example, have an optical lattice with a structure which is arbitrary. For example, if you take an optical lattice which will in 1D create a potential something like this, with the spacing between them is lambda by 2, that is, let's say 532 nanometer, with the laser what we have is 1064. Now this may be limiting us for many experiments.
Okay.
Suppose you want the spacing to be dynamically varied during an experiment.
Okay.
So with this MEMS we can do that. On the other hand, if we want to do this with the traditional optical lattice, we have to change the wavelength of the laser, impossible, because optical lattice is a stabilized potential, or you have to change the angle between the laser beams, which is also not very practical. So here with MEMS we can do it, and what you are asking is rather trivial, because we can always create whatever potential we want to create with the image. But you know that's
Yeah, actually why I'm asking this, there is one paper recently that area got developed, this reentrant localization. Yeah. in that paper they have described this cosine form, this quasi-periodic lattice, but they haven't said any kind of like what is the experimental things, because most of the papers they use cosine square, sine square.
Yes,
Yeah.
for example, in some sense, what you are saying is, wait a second, I have to go a bit back. Yeah, so for example, some long time back, when you use, yeah, why? For example, when you use this kind of quasi-periodic lattice,
Yes,
what
yes.
we used long time back, which also can be connected with Aubrey-Andre model.
Mhm.
So there, this is the standard technique. But now imagine that you can create a quasi-periodicity which is more random than what is provided by the Aubrey-Andre. Aubrey-Andre is a limited regime where the quasi-periodicity can be demonstrated.
Mhm.
So these are in some sense, what you are saying is reentrant superfluidity, right? Means you can go
Yeah.
from superfluid regime to an insulator regime and come
One
back.
second, yeah.
And so there are, so I'm not an expert, but these are experiment demonstration of the phase diagram where you can actually reach by just tuning one parameter, entering the superfluid regime, then going out of the superfluid regime, and then again so maybe more exotic phase diagrams can be produced
Yes.
depending on the.
Any other question from
Thank you, sir.
students? Okay, last question then.
I have a really naive layman's question. So in often all these measurements, quantum community, they settle down with the second order moments. I would believe higher order moments will be carrying more information.
Yes. Actually, yes, no, that's a very nice question. So, experimentally, it's hard. So, for example,
Measurement is tough.
yes, measurement is because even the second order moments
Second order
are
itself is
weak.
tough.
So,
Higher order, the
yes,
complexity
but
of the experiment, that is the main reason why people don't go.
well, not in
An
terms.
aspects group did measurement.
I know,
higher order.
only few groups in the world, they try this kind of things, but in
But
general, this trend is not there.
By
So
detecting
why
with
is the problem?
microchannel plate
I wanted to understand what is the problem
falling
basically.
atoms. Yes.
well, signals becomes weaker. See, once you look at the G2 or second order, you still have reasonably strong signal. I guess that's what you are asking. Now you want to go for a G4 or the possibility of having even at very low time simultaneous counts or lack of it is less. But as you said, there is a microchannel plate where BEC was allowed to drop, and you can see this was done with a helium, both helium 4 and helium 3, so they could show the Fermi and Bose statistics using that. But now the possibility of driving, see, for example, in a driven system, if you now want to see higher order moments, that signal may not be small. So that is one direction we have, especially in the context of spin system. I don't know how to construct an experiment for something else, but so this is actually an active program with the Bindu, where he can calculate the higher order moments and higher order correlation. But
Theoreticians can do that, but then experimental challenge, that is the main question.
yes, so my take is that we probably have to go to a driven system. If you look at a space experiment also, it is kind of a, well, I would not call driven system, but demonstration of the effect. But but Hongo Mandel and going beyond that's definitely a dream of an experimentalist. So
Thank you very much.